All right, Galileo studied motion by rolling balls down ramps. He rolled the ball down a ramp with a horizontal shelf at the end of it so that the ball was moving horizontally when it started to fall off the shelf. The top of the ramp was placed at different heights above the floor. That is, the length of the ramp varied, and Galileo measured the horizontal distance the ball traveled before it hit the floor. Here are Galileo's data. We won't try to describe the obsolete 17th century units Galileo used to measure distance and height. So the distance and height was, this is the data. So part A, make an appropriate scatter plot for predicting the horizontal distance traveled from ramp height and describe what you see. All right, so let's go ahead and do part A. So as you can see, I put in the data here where the height, remember the height was the height is going to be our independent variable, and the distance is going to be our dependent variable, otherwise known as the explanatory variable and the response variable. Let's go ahead and go back to our calculator. So what we want to do here is we can do, okay, so we're going to go to menu, we're going to go to statistics, we're going to go to stat calculation, and we'll do two variable statistics. So our x is going to be our height, and our y is going to be our distance. Okay, and the result is going to be in C. So as you can see, we have x bar is 705.6. So A, x bar is equal to 705.6. Let's see, the standard deviation of x. Standard deviation of x is equal to 267.501. And then we need a y bar. So let's go down. Y bar is 1228. And the standard deviation of y is equal to 265.917. All right, so we could actually, they'll give us the R here. So R is 0.9936, so R equals 0.993686. So this implies R squared, so you just square both sides, and that'll be 0.987412. Right? Okay, so I'm going to do the regression line manually, and then I'll show you how to do it in the calculator, right? So we know for the regression line, it's y hat is equal to a plus bx, okay, where b is equal to r times the standard deviation of y over the standard deviation of x, which we got to be 0.99386 times 265.91 over 267.5, and that'll give us 0.9878. So that's our B, and then our A is equal to y bar, so the mean of y minus b times the mean of x, which is 1228 minus 0.9878 times x bar, which was 705.6. And that'll give us 531.006. So that'll give us our regression of, so let's get our regression here. So this will be 531.006 plus 0.9878x. So this is our regression line for our table, right? So let's go ahead and go to the calculator. So let's go ahead and go to Menu, Statistics, Stat Calculation, and we'll do the regression. So we'll do the regression of the height as our x, the distance as our y, right? So we'll go up here. So you can see we have our regression now, where that A, we calculated it manually, but we can easily calculate it here. Our B, and then of course there's our R squared and our R, right? So there's our whole regression. So as we can see, alone, this is a pretty strong linear regression, right? 0.9936. So this is actually a pretty good indicator, right? And of course, we can do a graph. Okay, quick graph. And then what we want is we want to turn this to height and this to distance, right? So there's our graph. As you can see, it's pretty strong linear, but it's slightly curved, right? So this is where doing some different types of modeling might help, right? But we can even go here, Menu, Analyze, and we can do the regression, and we can do Show Linear, and there's our linear function, right? That represents this. Okay, so as you can see, we have our graph here, and there is a strong, slightly curved relationship between height and distance. So since it's slightly curved, what we're going to be doing is we're going to be doing different types of models to try to get it a stronger and stronger relationship, even though this one is pretty strong with that R being 0.993686, right? So next we're going to do an exponential model. So exponential. Okay, so what the exponential model is we're going to look at our y values, which in this case are our distance, right? Our y values, and we're going to take the natural log of them. Okay, so here are our y values. So this is approximately equal to 6.6846. Let me fix that a little bit. And this is, of course, when x is, so for 800, this is when our height is 300, right? So x is equal to 300. This is equal to 7.06647, where our x is equal to 600. This is equal to 7.1914, when our x, let me fix this, where our x is equal to 800. This is equal to 7.2004, with our x being equal to 828. And then finally, this is equal to 7.3132, when our x is equal to 1,000. All right, so now we have our new values here. So I'm going to go ahead and put these in the calculator. And then I'm going to see how this affects our new regression line under the exponential model. So as you can see, I have my height, my distance, and my e-distance for exponential model, right? So what I'm going to do is I'm going to look at the graph now for height and distance, right? Okay, so now I'm going to go to Menu, Statistics, Stat Calculations, two variable statistics for height for my x, and now for my exponential model, e-distance, right? And I'm going to have the result in D. So now this is my new regression for my exponential model. So I'm not going to worry about this stuff. My main concern is the regression, right? So it's 0.981409. So my R for this model is equal to 0.981409, which implies that R squared is equal to 0.963164, right? And of course I can do the regression model here as well, right? So I can go to menu, statistics, stat calculation, linear regression between height and e-distance, and this will give me my regression, right? All that stuff, that 0.963164, etc., right? So you can do the two variable statistics, or you can do that linear regression, right? So as you can see, let's go ahead and compare. R here is still not as strong as our first one, so the exponential model isn't the way to go, right? So now we're going to try another model. All right, so now we're going to look at the power model, okay? So what the power model does, so let's write power model. Okay, so we're going to take the natural log of our y value, which was all these. Okay, so of course these are the values that we had in our exponential, but for the power model, we're also going to do the natural log of our x's. Okay, so now these are our y values, natural log, and our x values, natural log, right? All right, so now you can see I put p height for power, right? So remember the e-distance, right, are these values here, and then the p heights are these guys here. So now I want to do a regression among these two for that power model. So let me go ahead and go to menu, statistics, stat calculation, and then let's go ahead and go to linear regression. And we're going to do it for the e-distance, or I guess the p height, right? And then the e-distance. Okay, so this r is 0.9986, right? So this one is r is equal to 0.998, which implies our r squared is equal to 0.9974. So comparing it to our first one, right? Our r was 0.9936, and now this one is 0.9987. So we can see the power model gives us a better regression, right? So we should choose the power model for to linearize a relationship. Does the relationship between distance and height seem to follow an exponential model or power model? So it would be following a power model, right? So for C, perform a least squared regression on the transformed data. Give the equations of your regression line. Define any variables you have or use, right? So now what I can do is for part C, since we're going to be using that power model, so A is equal to, so let's go ahead and go back to our calculator. So 3.75262, right? 3.75262, and then our B is equal to 0.515. There we go. 0.515, 183. So our regression, right? So our natural log of y hat is equal to 3.7514 plus 0.515183 natural log x, right? Okay, so that's our regression line where, of course, where y, the distance, and x is the height. All right, so this is our approximate distance given our regression that we've constructed using the power model, right? Okay, so now let's go ahead and do part D. Use the model from part C to predict the horizontal distance a ball would travel if the ramp was 700. All right, so part D, we know that ln of y hat is equal to 3.7514 plus 0.515183, and then this is going to be ln, right? Natural log 700, which we do this to get 7.12763. So now we have the equation ln y hat is equal to 7.12763. But we're interested in the height. We're not interested in the natural log of the predicted height, right? So what we can do is we can do e to the natural log of y hat is equal to e to 7.12763, because e to the natural log of y hat is just y hat. So our predicted value is going to be e to the 7.12763, which is equal to 1,244.53. So our predicted value for 700, right, which is not on this, right? So our predicted our predicted distance for a height of 700, right, is going to be 1,244.53. And this is how you do these types of problems. You just do a different type of modeling to try to get a better regression line. And once you get a better regression line, you can do more thorough analysis.